This is lecture 37. So in the previous lecture, we were looking into how to ensure that our circuit is our negative feedback loop is always stable, right? So all the good things about negative feedbacks are it gives us precise gain. It gives us a gain which is invariant to ambient temperature. It gives us a gain which is also largely invariant to load resistance RL. All are good, but one possible problem is it can lead to instability, and we saw an example of how it can lead to instability in the previous lecture. And so essentially, your V naught over Vi is 1 over H times GH by 1 plus GH. If we are assuming the negative feedback loop is of this form, right? This is also a critical assumption. If we assume that the negative feedback loop is of this form, then we can express V naught over Vi as a 1 over H times GH by 1 plus GH. And what is GH? GH is a loop gain. So essentially this becomes L by 1 plus L. Now, having gone through frequency dependent characteristics for so long, we know well that these L or loop gain are functions of S, right? They're dependent on frequency. And the examples that we saw where if we have a amplifier here, amplifier transfer function is obviously a function of frequency, because for example, the common source amplifier, it has capacitances at various places, and its frequency is and its gain is not same across frequency, right? And more importantly, we also saw that as the input changes, right, or rather as the frequency changes, there is some phase lag starts to build in between V naught and Vi, right? At very low frequencies, V naught, the phase of V naught is almost equal to that of Vi, but as frequency increases, the phase alignment between V naught and Vi also starts to differ. And we saw in the previous lecture that can lead to a potential problem. And what was the problem? If the feedback voltage Vf, right, if the phase of the feedback voltage Vf was exactly equal to 180 degree with respect to Vi, and also if the feedback voltage was of equal amplitude of that of Vi, then we end up building an oscillator, right? So instead of an amplifier, we end up building an oscillator. So that's not a good thing, right? So what was the condition that we wanted to avoid? We wanted to avoid, so for stability, we must avoid L of j omega equal to minus 1, or in other words, we need to avoid 1 plus L of j omega equal to 0, right? So if we can avoid this, or let me put in S domain, because we know S equal to j omega, we can put any time, right? So, so if we can avoid 1 plus L of S equal to 0, then we know that this guy will be stable, right? But we know one more thing, right? We know one more thing from our control system, basic control system understanding. The basic control system understanding tells us that for stability, we also must avoid, for stability, the stability of the closed loop system of V naught over Vi, right? For the stability of V naught over Vi, the poles of V naught over Vi must lie in the left half plane, the left half S plane, right? Okay, so what does that imply? This implies that the roots of 1 plus L of s must be or must not be present in the right half s, right? These are consequences of stability, right? So we know that poles have to be in the left half plane, but poles of what? Poles of poles of V naught over Vi. Note that not poles of L of s, right? So you have to ensure that the poles of V naught over Vi, that is the roots of 1 plus L of s, have to be on the left half plane, right? So let me make a distinction here and say that roots of 1 plus L of s, not L of s, right? That is an important distinction to make, right? So the roots of 1 plus L of s must be on the left half plane or must not be on the right half plane. So why are we saying this? We are saying this because long time back, Professor Nyquist came up with a very neat way of figuring out if the roots are indeed in the right half plane or not, right? So you might say that I can write out the polynomial, L of s will be some polynomial, higher order polynomial, and then I can find out the roots. Yes, in principle we can do that. However, the problem is if L of s becomes a polynomial of the order of 3 or higher, right, then you cannot have a closed form solution of the roots. Okay, so since you cannot have a closed form solution of the roots, you cannot develop an intuition as to whether my circuit will be stable or not, right? So that's why we need to figure out whether the roots lie in the right half plane or not. We are not particularly bothered about finding out where exactly the roots are. We are trying to figure out whether the roots are on the right half plane or not, right? So that's what we will do. We will let me take you through a quick refresher of Nyquist criteria from your undergraduate control system courses, and it essentially says the following. So let's say I have, this is the S plane, that is sigma j omega, right? So what are we looking for? We are essentially looking for the location of the poles of L of s, right? So if, let's say, the poles of L of s exist in the right half plane, right? So if the poles of L of s exist in the right half plane, let's say one pole exists, right? Then if I draw a contour, of, or forget about the contour for the time being, all it says is that so let's say a pole exists somewhere in the S plane, and I evaluate the transfer function for all values of S in a closed contour. Need not be a circle, in a closed contour. Then, and if I correspondingly plot real of L of s, or let's say real, so real of L of s and imaginary L of s, right? If I plot this, what will I get? So essentially what we are trying to say is that, let's say I select some point here. Okay, I select some sigma 1 omega 1 point, and I map this point on the L plane, right, on the L of s plane. Or let's say let's do one, let's take a step back and say that we are trying to find out this is the this is the real of 1 plus L of s. This is imaginary of 1 plus L of s. Okay. So all we are saying is that if for every point in the S plane, there will be a corresponding mapping point in the L plane, right? So essentially, I will probably have a point somewhere here, right? So maybe so this maps to this point. So let's say this maps to this point. Let's say I take another point somewhere over here. Maybe this maps to this point, and I map and take another point here. Maybe this maps to this point, and so on. And I keep on taking these points, and I go in a counterclockwise direction, right? So what will end up happening? I will end up coming back to the same point, right? I will essentially come back here, right, by moving in some contour in the 1 plus L plane. I will move in some contour, and I don't know what the contour is, but I know that it will be a closed loop. I'll come back. But what Nyquist showed that if in the S plane, right, if in the S plane the root of 1 plus L of s, the root of that function, right, exists, then what is going to happen? Then this closed contour in the 1 plus L plane must encircle the origin. Or in other words, what should happen is that in this case, the origin should be inside the contour, right? The intuitive way of understanding this is what is if let's say this is the pole, what is 1 plus LP? What is the root of 1 plus L of s? Yeah, what is 1 plus L of s at s equal to p? By definition, by definition 1 plus L, if p is supposed to be the root of 1 plus L of s, then by definition at p 1 plus L of s has to be 0, right? So in other words, this pole maps to the origin. Pole maps to the origin in the other plane, okay, in the transformed plane, okay. So if I take a closed contour which in the S plane which encircles the root in the S plane, then in the transformed plane I will also encircle the origin, okay. So that's what Nyquist told us, right? And then he further extended this finding and said that in stability cases, in while finding stability, all we have to ensure that the roots of 1 plus L of s doesn't exist anywhere in this entire S plane, right? So we have to ensure that for stability, no roots of 1 plus L of s exist here, right? We must ensure that this actually happens. So in order to ensure that, what do we need to ensure? We need to ensure that if we take a closed contour in the S plane, right, this is sigma, this is j omega, this is, let's say, 1 plus L of s. If we take, this is real, imaginary, if we take a closed contour in the in the S plane, right, like the way I have shown here, then if if a pole, if the roots of 1 plus L of S doesn't exist, then I should not be encircling the origin. Correct? So all it says that if, so maybe uh, I'll be doing something like this. Maybe I'll be doing, right. So it will do some funny structure, right? We'll have some funny contour. So if no pole exists, then no encirclement of origin. Okay. Okay. So this, so by looking at the plots, we should be able to figure out whether whether we actually have a closed loop pole on the right hand side or not. If we have a closed loop pole on the right hand side, then we are in trouble, right? Okay. So now then we further say that instead of plotting 1 plus L of S and trying to figure out whether we are encircling the origin or not, let's plot L of S and try to figure out whether it encircles minus 1 or not, right? They are essentially the same thing. So in other words, what we are saying is, instead of uh, plotting 1 plus L of S, let's plot L of S and say this is real of L, this is imaginary of L, and instead of focusing on the origin, we'll focus on the point minus 1 0, right? And we'll do the same exercise, and all we have to ensure is that if the contour, if the closed contour if the closed contour in the L domain does not encircle minus 1 0, then we are fine, right? That's all we are trying to ensure. Okay, so it further says that if we are doing a further offshoot of this is to ensure that we are moving in the right direction. By what I mean by that is, if we move, but since we are moving in anti-clockwise direction in S plane, we need to check for anti-clockwise encirclement in the L plane, right? So what I mean by that is that if, let's say, you find a contour which has a clockwise uh, uh, I think I made a mistake here. Yeah, sorry, this should be clockwise encirclement, right? So this should be, since we are moving in the clockwise direction in the S plane, right? This is, since we are moving in the clockwise, we need to ensure that we need to check for clockwise encirclement in the L plane, right? So let's say for uh, for for some transfer function, we moved in the anti-clockwise direction in the S plane, but when we came back to L plane, we found that it has an encirclement, but in the anti-clockwise direction, right? So that's, Nyquist says that that's not a problem, right? So this is stable, right? This is still stable. Okay, so we have to keep a track of whether the encirclement is in a clockwise or anti-clockwise direction. Okay, so this might seem a bit confusing if we without the aid of an example. So let's take an example and then try to figure out, right? Okay, so now when let's take an example of a first order system. Let's say L of S is equal to some A naught by 1 plus S by P1. Okay, So let's try to figure out what the Nyquist plot of this will be. Okay. So when we are doing Nyquist plot, what are you essentially doing? See, the smart thing about Nyquist stability criteria is this. So when we are doing Nyquist plot, we are starting from the origin and we are moving in the j omega direction, right? We are starting from the origin, we are moving in the j omega direction, and we are going to all the way to infinity, right? We are going all the way to infinity. So what happens to the transfer function in any realistic transfer function when we go omega to infinity? Because in any realistic transfer function, the number of poles is always greater than number of zeros, but especially it's kind of a low pass transfer function. Eventually everything has to go to zero. So if you go to infinite frequency, the transfer function essentially goes to zero, right? And then when you go to infinite frequency and for s equal to infinity, essentially you do this encirclement business. For this entire encirclement, the transfer function remains zero, right? And when you come back here and then you go from minus infinity to j to origin, you essentially are traveling that 0 to j omega plot contour or 0 to j omega line in the reverse direction, right? So in essence, all we have to do is to plot the transfer function between 0 to omega equal to infinity, right? That's the cool thing about Nyquist criteria. So let's do that. So if we do that, what will happen? So this is L of S, this is L plane, L of S plane. Okay, and what is the point that we need to avoid? We need to avoid this minus 1, 0 point. This is real, this is imaginary. Real of L, imaginary of L. Okay, so what is, as we traverse the j omega axis, so we have to put s equal to j omega, right? So your L of j omega is equal to a naught by 1 plus j omega by p1, right? So mod of L is a naught by under root 1 plus omega square by p1 square, and angle of L is minus tan inverse omega by p1. Okay, fine. So let's start. So let's say we start from omega equal to 0, right? If at omega equal to 0, what is mod of L? Mod of L is a naught. If a naught is high enough, it's completely real. It will be somewhere in the right hand side in the L plane. Okay, and then if I increase omega, a naught will decrease, right? So we have to, it will probably come to the left hand side, but will it come to the left hand side this way or will it come this way? Will it go up or it will nosedive? So from where can we get that information? We can get that information from the angle, right? So what is the angle now? Angle is negative, right? So the angle is negative, which means it's going down, right? So that's good. So let's go down, right? So this will go down, and at omega tends to infinity, what's going to happen? At omega tends to infinity, mod of L goes to 0, right? So it will go to the origin, but from what angle will it go to the origin, right? So it can go to the origin from this side, it can go to the origin from this side, it can go to the origin from this side, or it can go to the origin from this side. From which angle will it go? So clearly, if we put omega equal to infinity, then the angle becomes minus 90 degree. So which means that this plot will go to the origin using this contour. So this is when, right, this is when we have moved from 0 to infinity, right? So when I have moved to infinity, the transfer function is 0. So when I do this entire circlement, right, of the entire right hand side S plane, what will the transfer function be? It will still be 0. Then when I go from minus infinity to 0 along the j omega axis, what will I see? I will again see the same transfer function, right? But its mirror image, right? Because now essentially for whatever omega we had, we can put minus omega. It's the same transfer function, but its mirror image. So the transfer function will something look like this, right? So regardless of the shape of the transfer function or my drawing skills, all you have to appreciate from this is this guy is getting nowhere close to this critical minus 1 0 point, right? So since this is nowhere close to the minus 1 0 point, this is always stable, right? So this is always stable. Fine. We can understand this from the Bode plot also, right? So Bode plot of a first order system, what will it look like? Mod of L. So this is something like straight line till P1, and then it goes like this to minus infinity dB. And what is the angle of L? The angle of L will start from 0 and it will go to minus pi by 2. Since this is never going close to minus pi, right? So we can as well say that this guy is always stable. Okay. Okay, fine. So by the way, where is this minus 1 0 point in the Bode plot? So when I say minus 1 0, what do I essentially mean? It means the magnitude of loop gain is 1 and the angle of the loop gain is pi, right? So where is this where does the magnitude of the loop gain go to 1? We have to, if this is a 0 dB line, so the magnitude of the loop gain goes to 1 where the loop gain crosses the 0 dB line, and that frequency at which it crosses is called unity gain frequency, right, or omega UGB, right? So the frequency at which L of S or L of j omega, mod of L of j omega goes to 1 is omega UGB, right? So or omega U. So we'll use omega U in this course. Okay. Okay, fine. So what we need to check? We need to check that whenever the gain becomes unity, what is the phase? If the phase is pi, then we have a problem. Pi or minus pi, we have a problem. When the gain is unity, phase is not minus pi, we don't have a problem, right? Okay, fine. So clearly in a first order system that is not possible, so we are safe. What about a second order system? So let's say L of S is A naught by 1 plus P1 1 plus P2, 1 plus S by P2, right? So let's plot the Nyquist plot once again. So what is mod of L? Mod of L is A naught by under root 1 plus omega by P1 squared times 1 plus omega by P2 squared, right? And what is angle? Angle is minus tan inverse omega by P1 minus tan inverse omega by, okay. So again at omega equal to 0, so this is L plane, right? This is L plane. Mod of this is real of L, this is imaginary L. So at omega equal to 0, where are we? We are far out on the real axis. This is A naught, right? So this is A naught. Then as you increase frequency, right, I am coming closer to the origin, but from which angle? I am again going down, right? But now at very high frequency, right, at omega equal to infinity, I know that we'll go to 0, but at through what angle I'll go to 0? I'll reach the origin at omega equal to infinity, you get minus pi by 2 from here, and you get another minus pi by 2 from here. So essentially you have a total phase lag of minus pi, right? So essentially you will reach 0 from the third quadrant, right? So essentially this will do something like this. And if we have minus 1 0 point here, you can see that we are kind of getting closer to trouble. Okay, so we are still not encircling, but we are getting closer and closer to trouble. Okay, so now when we are getting closer to trouble, we need to ensure that how far are we from the trouble. Okay, so how do we ensure how far are we from the trouble? So as it turns out, people have figured out a way of quantifying that exact thing, and the quantification is as follows. So ultimately we have to ensure that wherever we are away from this minus 1 0 point, and whenever we are cutting this minus 1 0 point, right, this frequency, the frequency corresponding to this minus 1 0 point is omega. So the frequency to the frequency corresponding to the intersection point of the contour and the unit circle, right? So when I say unit circle, what do I mean? What I essentially did in this case is I drew a circle of magnitude of 1 centered at the origin, right? So whenever you are cutting this point, what is the magnitude of this radius? This radius is 1. So wherever you are cutting this point, I know the loop gain is 1, right? So the frequency corresponding to the intersection point of the contour and the unit circle is omega u, right? That we can also get from Bode plot. And the angle, right? And the angle that we are away from the minus 1 0 point. So this, let's say this angle is theta. So theta is the angle, or theta is the margin in phase that we have before the system crosses minus 1 0, right? In other words, if we take this system and give it an additional phase lag of theta, I will end up cutting the minus 1 0 point, and if we get slightly more phase lag than theta, I will end up encircling the minus 1 0 point, right? So then our system will become unstable, right? So this margin is often called, is more popularly called phase margin, right? So this margin, the margin in phase, or let me write it in a more formal way, the excess phase that causes the L of S contour to encircle the minus 1 0 point is called the phase margin. Okay, so what are the steps to find out the phase margin, right? So the steps to find out phase margin is, number one, find the frequency at which L of S or L of mod of L of j omega cuts the unit circle, right? Okay. So in other words, i.e. find omega u. Okay. Step 2 is find the phase at omega equal to omega u. Step 3 is evaluate the amount of excess phase of x or amount of additional phase that is required for encirclement. This additional phase is phase margin. Okay. So again, I mean, it's better shown with an example than writing it in words. So let's do that, and that will help us in our understanding, right? So let's do the same second order transfer function in terms of that the Bode plot. In terms of Bode plot, let's say L of S is n0 by 1 plus S by P1 times 1 plus S by P2. Okay. So if I sketch a Bode plot, so what should I see? Mod of L, I should see somewhere. I should see. I would know the locations of the poles in advance. So let's say this is P1. Let's say this is P2. So I will sketch the transfer function, right? I will sketch the transfer function something. So this will be something like this. Okay. And the phase of this will also be to start from 0. It will go like this to minus pi by 4. Then roll off to minus pi by 2. Then and this will go like this. Okay. So what is the step 1? The step 1 is to find out omega u, right? So in other words, the step 1 is to find out where this L of S plot cuts the 0 dB line, right? So how should I find that out? So this seems to be a piecewise linear plot. So how should I find that out? In order to find in any piecewise linear plot, we have to take a piecewise, we have to find out solutions in each of the line segments, in each of the possible segments, and go back and see whether the solution makes sense or not, right? So what is the equation of L of S when omega is less than P1, right? So L of S for omega less than P1 is equal to A0, right? Because this is A0. So if A0 is greater than 1, which obviously it is because we are making an amplifier, so clearly your omega u, or the unity gain frequency, doesn't reside below P1, right? So that's good. So what is the equation of L of S when omega is greater than P1 but less than P2? So this will be A0 by S by P1. So if the unity gain frequency lies in that somewhere here, right? If the unity gain frequency lies here, let's say if this is omega UGB, if this is omega U, this point, right? Then what should I see? I should be able to equate A naught by omega U by P1 to 1, and I should get a solution of this omega U which is equal to A naught P1, and this A naught P1 has to be, so if solution exists, then A naught P1 will end up becoming less than P2, right? If the solution doesn't exist, then A naught P1 will end up more than P2, which means my initial assumption will not be correct, right? And if this is not correct, then obviously the omega UGB exists. So this means that omega U does not lie between P1 and P2, right? And if this is not true, then obviously you have to evaluate L of S in the third segment. So L of S for omega greater than P2 is A naught by S squared by P1 P2, and if omega UGB lies here, if omega U is greater than P2, then the solution will be A naught by omega U squared by P1 P2 will be 1, which means omega U will be under root of A naught P1 P2, right? So this way we can find out omega U, right? So let's say we found out omega U, and let's say the omega U we found out is somewhere here. Okay. So what should we see then? We should see the phase. We should see the phase associated with omega U, right? Phase associated with the transfer function at omega U. So step 2 is find phase. So angle of L of S at S equal to, or at angle of L of j omega at omega equal to omega U, which is minus tan inverse of omega U by P1 minus tan inverse omega U by P2, correct? Okay. So maybe that is somewhere here. So we get this phase. This is this angle omega U. Let me use a different color. So this is the angle at omega U. So how much margin do I have? I have this much of margin, before which, right, if I push this, if I keep the magnitude plot identical and I push the phase plot down by this much amount theta, right? So then at omega U I will be getting a phase of 180 degree also. That is, I will be cutting that -10 point, and that is unacceptable, right? So how much margin do I have? So the margin is the phase margin that I have. The phase margin in this case is how much? This theta. The theta is this minus, or let me write it in a more generic term. This will be angle at omega U minus of minus pi, right? Because this is minus pi, right? And this is the angle. So the angle minus of minus pi is your margin, right? So essentially the margin that we have is pi plus the angle at plus the angle of the loop gain at the unity gain frequency, right? Right. So if we can ensure this, then we are good. Else, I mean, if we can ensure that this phase margin is positive, right? If phase margin is positive, system is stable, right? So if phase margin is negative, system is unstable, right? So note that, again, let me put in a caveat. The analysis that we have done in this case is for, this is for all pole systems, right? So strictly speaking, this analysis is true for all pole systems. However, we will also be using this similar analysis even if we have, even if we have zeros, and we'll see that going forward, right? So to summarize whatever, what did we do till now? We saw that a negative feedback system is susceptible to instability, right? We saw that using intuition, and the intuition was, if whatever, uh, if in the open loop case, if the return voltage is exactly, or is exactly equal in magnitude to the input voltage but 180 degree out of phase, then our system can become unstable, right? Then we related this condition using a Nyquist stability criteria, and we said that we need to avoid encircling the -10 point in the phasor plot of L of S or L of j omega, and then we move to Bode plot, right? Because Bode plot is much easier to plot using pen and paper than a Nyquist plot, right? So we move to Bode plot, and we said that we will use a 3-step process to figure out if the system is stable or not, and if it's stable, how much margin do I have for stability, and what is the criteria that we use. We essentially said that we will find out we'll find out the frequency at which we are getting unity gain, right? So this is like unity gain frequency. You have to find out at what frequency we are getting unity gain, right? Then we find out the phase of the transfer function at that unity gain frequency, and then we figure out how far we are from -180 degree point or -180 degree phase at the unity gain frequency. That difference is the margin, and that margin is phase margin. Okay. So it will become clearer as we do more examples, and that is what we are going to do next. Okay.